Okay, so let's get these screens out of my way and share my screen. All right, so welcome everybody. So I'm Andrew Toivonen from the University of Minnesota. I'm a fifth year graduate student and a LIGO member. So, I work on low latency and in general the dissemination of alerts and data products from gravitational wave candidate events. And in particular, I have an MMA lean, so I'm interested in, neutron star mergers, NSBHs, things like that, with the hope of finding a kilonova. So I'll get started. A little bit of background about gravitational waves and multi-messenger searches, right? So in general here, and I'm sure many of you are familiar with this, but we're looking for sources of gravitational waves. And as far as we've seen so far, right, those have come from what I'll refer to as CBCs, or compact binary coalescences, which are mergers of compact objects, so neutron stars and black holes. I'll talk about BNS, which is binary neutron star merger, BBH, binary black hole merger, and NSBH, neutron star black hole merger. I'm particularly interested in the candidate events with the possibility of having a neutron star, so the BNS and the NSBH type, as they're potentially able to produce a kilonova. So how do we actually detect these gravitational waves? Well, we have a Michelson interferometer with 4-kilometer arms. And so what this is essentially a big laser underground, which this laser is beamed out, split at a mirror into the two arms. And we have this L shape, these two arms, so that we have some sort of directionality in terms of detection. So we can localize these events in the sky, which is also why we have multiple interferometers. But essentially what happens is this laser is split and then bounced back and forth a bunch of times in what's called these Fabry-Perot cavities. I think it's 200 to 300 times that this laser gets bounced back and forth, which extends the path length of the laser, right? It's like effectively making the arms longer. And then what we're looking for is when you actually combine the lasers back together, we normally combine them directly out of phase with destructive interference that we don't see any light. We combine them perfectly out of phase. But when a gravitational wave passes through, it actually stretches and expands space and time, which means the path length of the laser, the path length between the two mirrors actually changes, and you end up then recombining signals that are slightly out of phase, and you let some light come through. And so then what you're actually detecting is how out of phase these two arms are when that gravitational wave passes through. And the main thing with this is it's a sensitivity problem. So you need to be really, really sensitive to small changes. They say we're sensitive to changes in distance approximately 1/10,000th the width of a proton. Or they say it's like measuring the distance to the nearest star, which is, 4 and change light years away, down to the width of a human hair. So again, this is something that, this was theorized a long time ago, but it's a sensitivity problem to actually detect these, and it's really cool that we can do so. So where are these detectors? Well, we have Hanford in Washington State, Livingston in Louisiana, and then Virgo in Europe here. Kagra is in Japan, but it is not operational right now. They're hoping to join the run some point, which we'll see what happens with that. So what do gravitational waves actually look like? We're going to be talking about source classification, right? So we have to make some sort of, delimitation between BNS and BBH and NSBH events as well. And so GW 150914 was the first direct observation of gravitational waves. It was a pair of 30 solar mass black holes. And so what you see here, if you're looking at plots like this, which again, some of you might be familiar with, but on top here, we're looking at the strain, which is essentially in distance of how much the path length of the laser actually changed. And so you can think of this as that wave comes through, you're seeing it stretch and expand space and time, hence the change in strain. And the reason you see this kind of characteristic wavy shape going up to a peak here is because these are two objects that are dancing closer and closer together in an in spiral. And so as they spiral and spiral closer together before actually merging, you're seeing the frequency and amplitude actually increase there. And so then if you look at that in frequency space here, which you do see on the bottom, which is often how we'll look at these because it kind of simplifies things, you'll see this characteristic chirp shape, as we call it, which you see that it actually just ramps up in frequency, just like you see in the actual plot of the strain above. And so, BBH chirps are audible for, maybe about a second, often less. You see here, we're looking at maybe more than, 1/10 of a second here. And obviously, this is what we can see with our, eye. Obviously, it's probably detectable for a little bit longer. But just keep in mind that this, in BBH, we're talking about 1 second for the chirp or less. And so, with this detection, obviously this opened up a new field of gravitational wave astronomy and all of this interest in, a new way of looking at the universe. Okay, well, what about BNS, right? That's what many of us are interested in. So GW170817 was the first BNS observations, and this chirp was audible for about 100 seconds. This is a much longer in-spiral phase as the two objects dance around each other. And so this was observed in Hanford and Livingston, the two detectors, and there was actually a Virgo, you don't see it in Virgo non-detection, which actually can help with the sky localization, the sky map, as I'll talk about later. And this was an event that was constrained to about 30 square degrees in the sky. So, in the world of gravitational wave, astrophysics and following up these events, that's pretty good. We can do better, but it can also be a lot worse. But 30 square degrees is not, not a small area in the sky, and it's not a small feat. And luckily, there was a detected GRB and whatnot. But in general, right, these are going to be large sky localizations, compared to some sort of other, transient or other type of, astrophysical events that we'll have to canvass the sky with surveys, right? And so we'll have to try and, cover that sky localization as soon as possible. We want to get our alerts out as soon as possible so that we can cover that entire sky. And, an important thing from this was that we observed the kilonova, and actually our process material was observed, which is essentially how the heavy elements in the universe are expected to be produced. And I'll talk a little bit about that. Okay, and I mentioned this, right? And we're talking about source classification here a little bit. So how do we actually determine what we're looking at? So how do we delineate between, BNS, NSBH, BBH? Well, BNS and NSBH have longer signals or chirps, as I've been calling these chirps, due to the longer in-spiral phase and actually the smaller RESCO, which is the innermost stable orbit. And so we can determine chirp mass and more by measuring the frequency and frequency evolution of the signal. So the chirp mass is the thing that's actually the most easily measured by the detection of gravitational waves. And maybe I should have put a chirp mass formula up here if you're not familiar with it. But it's essentially a sum over a product of the masses raised to some powers. And so it's the reason we use this quantity chirp mass is because it's actually directly measurable from the gravitational wave signal. So it's like what we actually can observe most easily from gravitational waves, and that's why we use this quantity. Determining the actual individual component masses, or the ratio between them, the mass ratio, is much harder. And so we'll get into that. But this is kind of the reason it's hard to sometimes determine exactly what it is, which we'll talk about with the DM event. Is because the chirp mass is what we measure well. So it's kind of like, a total mass sort of measurement. We measure that very well, but we don't measure the individual masses super well. So, okay, multi-messenger searches, right? Like, so obviously since GW170817, it's been an explosion of interest in all these searches. And in general, the goal, right, is coincidences between gravitational waves and EM, whether it's GRBs or kilonova, as well as neutrinos. And kilonova, so again, we're probably familiar with this. These are the astrophysical transients that may result from BNS or NSBH mergers. They can be accompanied by a short or long gamma ray burst, and they decline pretty fast. And that's the main thing. They're relatively faint in terms of you have to have targeted searches for these, right? They're not just gonna show up in the sky like a supernova could, right? And then you have some early time blue or UV, which is RNI bands, and late time red or near infrared. Okay, and why do we care about this, right? What can we actually learn from these multi-messenger observations, which is combining the gravitational waves with the actual EM observations, or neutrinos? But first one, heavy elements nucleosynthesis. So how are heavy elements created in the universe? So these are elements heavier than iron, and can we observe these R process elements in the neutron star mergers? And so why is this important? Well, you may be familiar with this, but only elements up to iron can be produced by even the most massive stars through fusion. So fusion is only energetically favorable up until iron, and then it takes energy to actually combine these, or to fuse these elements together. So what I'm saying is, up to iron, right, it's energetically favorable to fuse things together, and after that, fission becomes energetically favorable. And so that's why you'll see that there's this question of why where do these heavy elements come from in the universe? How are these elements heavier than iron produced? Which is probably and most likely, supernovae and neutron star mergers like this. And it has been observed that there was R process material observed from these neutron star mergers. The next thing would be the neutron star equation of state. So what's the pressure density or mass radius relation in a neutron star? And this is essentially just probing nuclear physics and understanding how matter behaves at the highest energies and densities. And then estimates of the Hubble constant. So can we measure the expansion of the universe? And can we ease the Hubble tension? And I'll talk a little bit more about each of these, right? So if you're not familiar with this, our process nucleosynthesis is the rapid neutron capture process. And it refers to a high neutron capture rate compared to the beta decay rate. And so this is a nuclear periodic chart, protons or Z on the y-axis, neutrons or N on the x-axis. And what you see here is rapid neutron capture, which I'm going to put these arrows here to show you kind of what's going on here. But maybe I take one step back and say, you imagine you have this neutron star, which you can think of like one big nucleus. And unsurprisingly, based on the name, right, it's mostly neutrons. And so you have this neutron star and it collides with another neutron star. And in that merger process, some of the matter is actually ripped off. That's called the mass ejecta. And this is what's actually going to lead to the kilonova. The more matter that's ripped off, the more mass ejecta, the brighter that kilonova will be. And so this mass ejecta is ripped off, and now you have a whole bunch of essentially free neutrons that are now in rapidly expanding and undergoing a whole bunch of nuclear reactions. And so you have nuclei that are undergoing neutron capture, which obviously is just collecting another neutron, which obviously moves you this way. And then you have beta minus decay, which it happens in unstable elements when you have too many neutrons essentially, and a neutron decays into a proton and an electron and an anti-electron neutrino. But this is how then you can actually move up this periodic chart because you're capturing a whole bunch of free neutrons, and those neutrons are decaying or popping into protons, which moves you up this chart. And then you have fission that will slow you down and split things apart and move you back down. But in general, it's this rapid neutron capture and beta minus decay that allows you to kind of zigzag up this chart and access these heavy elements. Okay, neutron star equation of state. Why is this relevant to this? Well, GW170817 mass radius posteriors can be used to constrain possible equation of states. And so an equation of state is going to be a curve on a mass radius plot like this because it defines the relationship between the mass and radius, or the pressure and density. And so here are our posteriors, our likely region that GW170817 falls within. And you can see a couple of named example equation of states that are in the literature and how they're consistent with it. More observations are obviously needed to constrain this and to make further limits here. But one other thing that's important about the neutron star equation of state is it does define the maximum mass of a neutron star, or the point between the neutron star and a black hole, right? So how about the Hubble constant? Something called a standard siren is when we can make a Hubble constant estimation of the from a neutron star and from a multi-messenger observations of a neutron star merger, right? With gravitational waves and EM observations. So to measure H naught, we need both a distance measurement and a redshift measurement. And so how this is done is we can estimate the distance from the actual evolution of the gravitational waveform. And then the redshift can actually be measured from the host galaxy if we're able to find an EM source. So imagine we find the kilonova, we locate it in the sky. We can then use the distance information to help place it in the galaxy, and then we can use galaxy catalogs, which will actually have the redshift measurement. And those galaxy catalogs, use the distance ladder, so they, there's all sorts of ways that we can try and measure the distance of those galaxies. But for example, standard candles like Type 1a supernovae are one way that we have these sort of measurements. You can technically do this with the gravitational wave only. That's called the dark siren method, but that's difficult, and it relies on you actually placing things in the galaxy, placing the source in the galaxy without actually finding the host, which means you have to rely on a sky localization and then marginalize over sky position and distance, just meaning you have large uncertainty. So it just doesn't work as well. But this plot here kind of shows, what we call the Hubble tension, which is the fact that Planck and Schu's, right, two measurements of the Hubble constant actually disagree. They're not even within each other's error bounds. And so Planck is kind of from our understanding of cosmology in early time universe with the cosmic microwave background, whereas Schu's is more measurements of the local universe with Cepheids and the standard candle Type 1a supernovae. But you see that they disagree. And we can make a measurement from GW170817 alone, Obviously, you can see the error bars doesn't really help ease this Hubble tension at all, but you could see that with more events, we'd be able to do that. Okay, so on to actual gravitational wave searches. We've talked about kind of why we care and brief differences between different sources, but now let's talk about how we actually find these. So we have two main types of searches, CBC, which are modeled searches, and these are match filtering pipelines. And so they are specifically searching for gravitational waves similar to templates, which would be CBC. These are compact object merger waveforms that have been generated based on our understanding of general relativity. And so we actually, how this works is they take the detected waveform and they actually match it to a template bank, right? And try and find the highest SNR between the template and the actual waveform that they've observed. So it's like, you take what you observe and you try and match it to a grid of a whole bunch of predicted waveforms. And then you have burst searches, and these refer to unmodeled searches. So they are essentially looking for coincident power in multiple gravitational wave detectors at the same time. And they don't specifically look for mergers of compact objects. They don't specifically look for any type of source class or make any sort of source classification. They instead are just looking for gravitational waves. They're just looking for coincident power. They're looking for the same thing to happen in two different detectors at the same time. And then finally, you have something like Raven, which is searching for external coincidences between gravitational wave and external events, right? So it's trying to match gravitational wave detections with EM observations or neutrinos. Okay, so as for these modeled CBC searches, and there's some background noise. Let me close my door here. Sorry about that. I'm not sure if you could hear that, but I could hear it. So I wanted to quickly close that. Okay, so we have modeled searches, right? Referring to searching for a specific waveform, right? So from these compact object mergers, specifically of neutron stars and black holes. And what they actually have is what's called a template bank. And you see this in an example from one of the searches, and you have a template bank in chirp mass, if you remember. And this is chi effective, which is the effective spin of the mergers. Of the two objects, right? So each object will have a spin, and then you have an effective spin, which is relative to the orbital angular momentum of the actual merger. So are the spins aligned and have direction of in the same as the angular orbital momentum of the merger, or are they anti-aligned, and etc. Which is relevant for what the waveform looks like. And so then, they essentially, and I won't get too much into this, but they essentially, have this grid of templates, and they match the actual observed signal to what's within here. And you can see how, I mentioned that, chirp mass is what we recover well. Obviously, again, this kind of points to, the difficulties with actually determining the individual component masses. And so you can imagine that, I showed the same plot of the strain from one of the first slides, and you can see how you could imagine you're matching what you observe, right, to some sort of a numerical relativity simulation here, right, which would be one of these lower ones, and you're trying to match up and find the highest SNR match between them, signal to noise ratio. Okay, unmodeled searches. So this is another way that we can do this, and these are searches for gravitational waves from undefined sources or morphologies, right? So again, we're not looking for this chirp signal. We're just looking for anything that is loud and happens at multiple detectors at the same time, right? So instead of looking for something that we expect to see, know what it looks like, instead we're just looking for the same thing at the same time in multiple interferometers. Because, it's expected that you could see gravitational waves from other types of sources besides, CBCs, and we hope to do this in future generation detectors like, maybe supernova, core collapse, etc. And so, we're just looking for anything that's out there. And these can also see CBC events, but they don't provide any source classification or determination of the source, because they pretty much just say, okay, we saw this much coincident power at this time, and they don't have, any sort of way to say, oh, we found this, right? Which would be, a chirp mass and a effective spin. Okay, now onto what you probably have been waiting for, which is S250206dm. And so obviously this was the event from the beginning of this month. And it had, by Piastra, we gave it a 55% chance of being an NSBH, 37 of being a BNS. And this was an exciting subject of extensive TOO, of target of opportunity searches. And so this was detected in two interferometers. H1 and L1. And we see that the original sky map and distance estimation put it at about 430 megaparsecs. Um, and so this is a really, really, really large distance and kind of at, to some degree, the edge of our gravitational wave sensitivity even. And so this is, like I said, very distant compared to something like GW170817, which was, a tenth of the distance at something like 40 megaparsecs. And it wasn't super well localized originally. If you remember, I quoted I think it was a 90% region of about 30 square degrees for GW170817, where this one's all the way at 2000. And so the sky localization can improve over time, but there's a number of things going on here. Obviously, first, it's very far, right? This just makes it hard for everything. Hard for the gravitational wave searches, hard for the EM searches, and hard for sky localization. In addition, we only saw this with H1 and L1. We can get really, really nice sky localizations, less than 100 square degrees, or better, when we can include Virgo information. But this is really just too distant for the less sensitive Virgo. And we do fold it in at the end with offline analyses, but for online, in low latency, immediately sending out that alert, this is essentially just too far. And it was found by multiple CBC searches. PyCBC is the preferred event right now. MBTA was actually the initial preferred event, and that can flip-flop based on we have multiple searches, right? So we have PyCBC, GST-LAL, MBTA, as I showed in that other slide. They all work together to upload templates, and then we select the highest signal-to-noise one, essentially the best one to be the one that we send out to the public. But sometimes over that portion, as people are uploading events, that can flip-flop, right? So you can originally send out an alert that has a slightly different sky map and sky localization and p-astro information, and then when we get a better match to someone else's template bank, we'll update that. Okay, so what actually happens upon the detection of an interesting candidate event? Like, what do I do? How's this all fit together? Well, I am trying to be, right in the middle of, we detect a gravitational wave, and I want to talk to astronomers and, give them the best estimation of what this is, where it is in the sky, and if they should take a look at it. And so I have alerts on my phone 24/7 for HAZNS type events. I wake up in the middle of the night when one of these is detected, and then I'll get on a Zoom call with my collaborators at, Caltech and ZTF, as well as Growth, which, there's telescopes around the globe looking for these. And so I'll join this Zoom call and discuss with astronomers whether this event merits target of opportunity observations, right? Should they trigger their telescopes? And in the case of 250206dm, this was a resounding yes. I took a look at this event, and right away it was like, this is great. We have a BNS NSBH, which we have had a bit of a drought of, obviously, during the observing run. And this looked like a real event, and almost for sure has a neutron star. The only really unfortunate part was like, well, this is really far. So it's still worth looking at. With complete honesty, I was very skeptical that we'd be able to obviously, see, observe essentially a kilonova from this. As you've seen, we don't have any great, candidates. We don't think that we have found a kilonova from it because it is too far. But this was one that had a solid chance of producing a kilonova. And if it was closer, we may well have seen it. And obviously, again, you're astronomers, these things, but what are some of the considerations that we also have to take into account for observing these would be, sky localization, how large is the region in the sky, and then things like weather, distance, and likelihood of astrophysical origin. But this was one of those that it felt very much like it's real, it's has a neutron star, so it could produce a kilonova, and I know it's far, but let's give it a chance. That's kind of the thought with it, with an event like that, if you really want to really simplify your discussions. Okay, and so sky maps, this is another thing. So you'll probably see, and if you follow these, you'll see the sky localizations that get put out by a collaboration. And you'll see that they will change over time, usually getting better, luckily. But what actually causes those changes in sky maps? So first, changes in preferred event. I talked about how, we upload these events essentially as soon as we see them. All the pipelines, upload these events very quickly. Often we're sending out an alert within 30 seconds. Which means that sometimes events are still getting uploaded as we're sending out an initial alert. And if somebody uploads a better template match, the preferred event can actually flip-flop, which means that we now have a different estimation of things like p-astro, the probability of astrophysical origin, which also tells you the source classification. Is it a BNS, is it an NSBH, et cetera. P-astro is what you're seeing up here when you're looking at this. And it can change the sky map. And so what else can affect these sky maps? Well, we have the low latency estimate, which is Baystar, which is very fast. Again, this is out within 30 seconds, right away with the initial alert. It's essentially immediate in real time. And then we have Bilby parameter estimation, which is much slower. And this is on the time scale of hours. I think, for this event, it was out within, an hour and a half, which is still very, very good. But it's more accurate. And then you have additional analysis can be done of other interferometers, for example, Virgo in this case. Virgo didn't see it online, but there's things that can be done. Now, you can look offline and find maybe a very, very low SNR trigger in Virgo, one that didn't make the SNR cut for submitting events. Or sometimes if we can look and say, okay, well, we should have seen this and we didn't. Well, actually, the way that the gravitational wave detectors work is they can have blind spots based on their antenna patterns. You can actually include non-detections, meaning we should have seen this, we didn't, which is actually done with GW170817, which allows you to rule out regions in the sky, meaning it can't be here because if it was there, we would have seen it. And then additional offline data analysis, including data cleaning, which was something that was done for GW170817 because there was actually a glitch in the data. Okay, so let's see, what does this actually look like in kind of in real time for something like this event? So this was the original first sky map that was sent out 30 seconds after merger. This was a Baystar sky map in low latency, and you see that we start with, let's talk about the median area because I think it's a little bit easier. We'll talk about the 50% area, right? So this means half of the probability in the sky is contained within 700 square degrees. That's initially what we had. So then the preferred event actually switched, and we ended up with a sky map that was 486 square degrees because we got a slightly better, a higher SNR event, a higher signal to noise ratio event, a better template match. We could see more of the signal. And this was less than 5 minutes after merger, this next sky map was there. So we already had made, a 300 square degree improvement within 5 minutes. And then an hour and a half later, Bilby had completed, which would be online parameter estimation. And you see this is, only what, a 30 or 40 square degree improvement here. And a slight, improvement, going the other way for 90% area. And then if we move on to the next Bilby sky map, and this was, online parameter estimation as well, this is starting to include some more of the factors here, which would be hopefully things like data cleaning and also analysis of additional interferometers like Virgo. We see that we're actually able to get this down to 222 square degrees. And then the last thing that's done is we actually run what's called offline PE, which is much longer parameter estimation runs that can include, manual intervention and, additional analyses, kind of like all those things I talked about on the slide. And finally, we were actually able to get this down, this 50% area, all the way down to 38 square degrees. This is 12 hours after merger, which does certainly, unfortunately, hamper the effectiveness, right? Because, this is 12 hours later. We've already been searching a lot of these regions that aren't now probably included in this sky map. But it does give us, a much better, estimation of this, and we get these things out, as soon as possible. All these analyses obviously take time. If it's an easy problem, then, obviously this wouldn't, this wouldn't be, all these things wouldn't be needed, right? And so you see here that these things will change and improve over time. But in general, luckily, these things are, they're improvements upon the previous sky map, right? So if you see, we're essentially just narrowing things down. And like I said, this one likely includes additional analysis of Virgo, whether or not they were, able to squeeze any sort of signal out of that or confirm it as a non-detection. And then the final distance estimation for this put us at, 373 megaparsecs, which again, this makes it very hard for detection of something like a Kilonova. If we're trying to see this, it's going to have to be, pretty deep, searches in order to be able to see this. Okay. So I'm going to move on to a little bit more about how we actually do source classification of these events then, unless there were any specific questions about DM before we move on. We can also do questions at the end. So, okay, how do we, what are our ways of source classification and how do we do these things? Well, we have P-astro, the probability of astrophysical origin, which is what you'll see. Like I said, those numbers you'll see on the event for something like, an NSBH, BNS, and then we also have the probability that it's terrestrial, which, could it be from a glitch or noise? And then we have EM bright, which is a very reliable way of classifying these things, but it doesn't specifically classify them by source class, like BNS and NSBH. It specifically provides a probability, is there a neutron star? is there a remnant, right? So has NS, is there at least one neutron star? Has remnant, is there mass ejecta, right? Was matter ripped off of the two objects, right? And remember, that's what produces a kilonova. You need that mass to be ripped off of the neutron stars. And then has mass gap, which means is there an object between 3 and 5 solar masses? And so, as you see here, we're pretty sure there's a neutron, or, we're essentially saying we're 100% sure there's a neutron star. And this does assume the event is astrophysical in origin, right? So it's not including this 8%. But we are pretty sure this was a real event. And this, like I said, has NS, probability of at least one neutron star, has mass gap. This would be, do you have something kind of in that borderline regime between a neutron star and a black hole? And the reason we care about this is because we expect, or, we just haven't seen a lot of these type of events. They seem to be rare, and that may be due to the, astrophysical channels that produce those low mass black hole type events. Okay, so how do we do these things? How's EM Bright calculated? Well, I kind of talked about this again already, but I'm going to leave them up here. You have has NS, probability of one neutron star, has remnant, probability of mass ejecta, has mass gap between 3 and 5 solar masses. And so this is actually done, this is a machine learning classifier that's trained on data from a simulation campaign. And what it actually does is it matches the actual true binary parameter space. So what the event actually is, whether that's a real event or an injection from a simulation campaign, and it maps that to the template parameter space. So the search, just like I showed before, when you had that template parameter space, it matches what they actually see in M1 and M2 and maps that to the real one. So it's essentially like a machine learning classifier that can learn the bias and uncertainties in the actual searches, right? And project that into, essentially a probability that you'll have, for example, a neutron star, or, have mass ejecta. And this uses, ejecta fits as well based on the, the masses of the objects. But it's taking essentially the output of the search pipeline and matching that to the true binary parameter space, which is pretty cool. And that's what allows us to have, a more accurate description of something like has NS. If you're looking at events and you're interested in, could this be something that has a, has a kilonova and something that's interested, this has NS is a super reliable and great quantity. It'll give you a great, and obviously has NS isn't saying there's going to be a kilonova, but it's saying there is a neutron star and you need a neutron star to have a kilonova. So this is kind of that first place to look. And then you can see EM Bright values across the parameter space. So this is the M1 and M2. These are parameter sweeps for a variety of spin values. And you can see here that you see how and so on the left here, and it should, oh yes, it's down here. P has NS. So this is the probability that there's a neutron star. Here's the probability that there's a remnant or mass ejecta. And what you see here is that in general, this is what we can observe, right? Or this is what we see, that in these mass regimes, right, we'll see, a neutron star, and here we'll see it has remnant. And this is from the, Deep's EM Bright paper, if you want to take a look at it. Okay, and then on to P Astro. So this can get a little confusing. So P Astro is actually calculated slightly differently by each search, using things like the SNR, the signal to noise ratio, the FAR, the false alarm rate. And this is false alarm rates calculated in general by estimating the noise background that we're seeing in when we're observing, right? So how much noise is there in the background, and then how much you essentially, when you detect a signal, you'll assign a false alarm rate. Maybe that's 1 per 10 years, which means that based on the noise background, we would expect to see noise as loud as this signal once per every 10 years, right? And that's just a quantification of that, the false alarm rate, how often we'd expect to see false triggers at this essentially SNR. And so then also using the template match, right, which gives you that chirp mass and effective spin information. And specifically, it looks at distributions of signal and noise events around a given chirp mass. So again, remember, you can measure that chirp mass pretty well. You can't measure the actual mass ratio or the individual masses super well, which is why you have these uncertainties. Is it, an NSBH or is it BNS? Well, it's because we've measured the chirp mass pretty well. We don't measure that Q, that mass ratio well, which is why we can bleed between, the NSBH and the BNS regime. And remember, all sorts of things are done to, try and match this to the best template, which would be things like, the chirp mass, the frequency and the frequency evolution and things like that. Okay, and a little bit more about actually sending out these alerts. I talked about this a little bit already, but how long does it actually take to send out alerts, and what do we send out alerts for? Well, in general, alerts are sent out for significant events, which are events that have a false alarm rate, which I just talked about, less than one per month. So we are trying to, false alarms are actually, inherently, something like this unavoidable. So we have to set some false alarm rate, some tolerance for false alarms, which is one per month. So we say that we expect to see about a false alarm, one per month. Um, and then we send out those alerts. And again, these significant alerts are the ones that you're often going to be getting alerts for and are going to be the target of opportunity observations, meaning people are going to slew their telescopes and look for a kilonova. But as I talked about, we send out this first preliminary alert within about 30 seconds, which is really great. And then parameter estimation is done anywhere between, a little bit over an hour and, a day or later for, certain types of events. But it's pretty cool that we can get out the initial alert within 30 seconds and get astronomers looking at things. So a little bit more about O4A and O4B, which is our current observing run. For example, in O4A, we had 81 significant events, 11 of them retracted. Remember this one per month thing, we do expect to see retractions. And a cool thing is we did introduce what are called early warning alerts. So these are alerts and searches where you're capable of sending out advance notice or alerts for BNS events actually seconds before merger time. And so we haven't actually seen a confirmed early warning event yet. We've had a couple of early warning alerts that were retracted, meaning taken back because they weren't actually followed by your normal full bandwidth, your normal searches like the CBC searches that I've been talking about. And this is something that in the future we hope to be able to actually give advance warning before merger. Say, maybe 10 seconds before merger, we can actually detect this event, and that would allow certain searches or things like Swift to maybe get on source and actually see the merger and the GRB and things like that. That would be great, and that's the point of this. Latency, I talked about this a little bit. I don't need to talk too much about this, but again, we're sending out we're trying to keep this median latency under 30 seconds, and actually we are doing well during the current observing run with that. And then finally, EM Bright, how do we do? What does this show us during O4A? Well, there was one standout event during O4A. You see, it was up here. It had a high HAS-NS essentially at 1, and a reasonable high as mass gap value. And that was GW230529. So this was not an event that was likely to produce a kilonova. Did take a little bit of follow-up and things like that. And there wasn't anything observed, but it's most likely a merger between a neutron star and a black hole, an NSBH event. And it's in this mass gap, meaning it's a pretty low mass black hole, which is kind of interesting. So they made this nice graphic about this, and this is pretty cool. This event, again, like I said, was in this HAS-mass gap, which is that between 3 and 5, which is why it's particularly interesting. Last couple of things here. During O4B, the cool thing is we do have, in fact, Virgo is online and joining the run, which can allow us to have much better sky maps. As I talked about before, the fact that you're looking at a 2 IFO sky map for DM does mean that it is going to be a larger sky localization. So right here, you can see this was from a simulation campaign, our paper here. You can see how the 3 IFO in green versus the 2 IFO in orange, which would essentially, you can think of this as, you can even just look at the red line for specifically H1L1. And you can see how this is a large difference. So the median here, if you're looking at the cumulative fraction of 0.5 here, goes from about 500 square degrees to 60 square degrees. So it's like a whole factor of 10 just for including Virgo, which is super important for us in terms of multi-messenger searches. We really need Virgo to improve our chances of finding a kilonova because 500 square degrees is just a lot to cover. And it's great because many O4B events have already been 3 IFO. Again, they can't be too far. We can't see them. But here's a 3 IFO example, and I already walked you through something like this. But you see how we started with the initial preliminary alert of 700 square degrees for the median. And by the time all this was done and we had a 3 IFO update alert, we were all the way down to 7 square degrees, which obviously this is night and day in terms of trying to make targeted follow-up observations. And so that's everything. And thank you for having me on this call, and feel free to ask questions.
Thank you, Andrew. I think you have a question in the chat from Siegfried.
Let me take a look. What are the most likely component masses for DM? So this is something that, we'll have to wait for parameter estimation. I can't really speculate too much on because essentially it's not my information to share because the way the collaboration works is we will release hopefully a single object paper on this that'll contain all of that information, and essentially like I said, that's simply not my information to share. But we do think, it's somewhere between this BNS and NSBH regime, and you have to stay tuned for that. Sorry about that. I wish I could share all this information. Are there additional plans to build? Yes, there are additional plans to build additional interferometers. Let's take a look. Actually, if I go back in my slides here, there's LIGO India, which is just beginning, I believe, construction. Let's see. So we are planning LIGO India, which will be super helpful. This is, I'm pretty sure it's pretty much a sure thing at this point, and it's going to take a while to build and everything, but LIGO India is planned. And then in the way future, there's something called LISA, which would be a space-based gravitational wave detector. So future generation things like that are also in the works, but probably more like decade plus out.
Could you explain more why? Obviously, there's a general understanding, but are there any specifics that people should know when how more instruments, especially interferometers, contribute to better localization?
Yeah, and so I think you want to think of it like triangulating the source, right? So like maybe maybe you could almost imagine you're in a big building and everyone's in a different room, and you hide a beeper somewhere and you can hear it going off, right? And everyone, you can say that this person in this room or whatever, and this is, obviously a loose analogy, but you can imagine that certain people will be able to hear it louder than others. And this is kind of how you can imagine like triangulating a signal. So the more detectors you have based on directionality and their L shape and everything, you can kind of point to where the signal came from in the sky. Does that make sense?
I think you had another question. That does make sense. Thank you. I realized I was muted. I think you had another question above Michael Freeberg's from Michael Richmond. He says, so we didn't find any counterpart aside from possible FRB to the S250206dm event.
There's some candidate. We do not have a likely, Kilonova, at least that I am aware of, that anybody has pointed to. Obviously, people were scanning through candidates and whatnot, but like I said, yes, unfortunately, I think this event was simply too far away.
Michael Freeberg asked another question. Any plans for Southern Hemisphere interferometers?
Not that I'm aware of. Like I said, I mean, so, LIGO India is the one that is the most, likely in the near future, which obviously is, reasonably close to the equator, but no, nothing that I know of in the Southern Hemisphere.
Dennis Marquet asked a very interesting question. Is DOGE, D-O-G-E, a threat for the operations of H1L1 and the next 05 run?
I mean, I think this is, I would say I think there's concerns across, all sorts of, funding and things like that, but not specifically that I'm aware of. I think this is something that hopefully will be, resolved, and we expect, hopefully continued funding for all these sorts of, events or all these sorts of projects, through NSF and other sources. But I don't have any specific real insight into that, to be honest.
There is a lot of there is a bit of tension in the air regarding everything that is funded either through government agencies or government supported science agencies like the NSF. So that is kind of where Americans are feeling that there is some tension there. Any more questions? Damien.
Maybe I have a question, if you allow me, Cristina.
Yeah, go for it.
Can you hear me well?
Yep.
Yes.
Yes, so thank you, Andrew, for this very detailed presentation. I have a question related to the follow-up strategy for EM observers, and especially our Kilonova Catcher astronomers who have usually, let's say, small field of view telescopes. No offense, but we have usually like less than 1 square degree field of view. And we have quite good sensitivity, I would say, but it's okay. It's like something like 20 mag, 21st if we can stack very long time. So I was just wondering if so we are always also in the professional area reviewing our strategy and especially knowing if we have to react to the first sky map or if we have to wait for a few hours, for example, to get the Bilby results and have a refined sky map, especially given the fact that the Kilonova signal will rise during the first hours, maybe a day will peak at after a day or several hours, several tens of hours. So we may have time to wait for a localization that is refined, and we may start to search for let's say galaxy targeting searches for several hours after we have a refined localization. So I don't know what's your opinion about this, and if we have to maybe wait for better sky map localization several hours after the trigger, or if you would advise to still let's start right away after the by star sky map, for example.
You know, thinking from a very practical, realistic standpoint, right? Obviously, you know, in terms of astronomy, waiting 12 hours for something, you know, is hard because, you know, only half of that's right going to be, you know, at night when you can observe essentially. So, you know, if it's good weather and it's, you know, at night a time, you know, wherever you are that you can observe, I think you should start observing, starting with the highest probability regions of the sky map. And obviously, you know, if it's maybe just you know, just before, let's say, dusk or something like that, and you want to wait for, you know, the next sky map to come out or things like that, that is something that, you know, is certainly, you know, valid. But I think because of practical constraints, right, which would be, you know, like I said, when can you actually observe and weather and things like that, you usually just want to try and maximize the time that you have. If you want to get a good idea of, you know, what should you expect to see in terms of a timeline for updates, right, you're usually, wait, I went the wrong way. Let me go back to my slides. It's very consistently that you're going to get this first sky map, right, with that initial alert in that first 30 seconds. If there's a switching of the preferred event, that should be within 5 to, you know, maybe even 10 minutes. And then you're probably going to wait about an hour and a half. And so you should just keep these sort of timelines in mind. If you're, you know, essentially where you are, you know, if you can actually observe at these times, and will you be able to observe in 1 hour, or will you be able to observe in, you know, when by the time offline, which is, you know, can take anywhere from 12 hours to, you know, a day. So that's kind of what I want to think. You want to think about, you have kind of that initial one within 30 seconds. It's fine to wait that extra 5 minutes to see if the preferred event switches at all. And then you know that your next updates are going to be coming on the order of 1 to 2 hours and then like 12 hours to a day. So those are kind of the timelines you want to think about. And it's just about maximizing the actual opportunities you have within those timeframes, right? I mean, I'm of the mind that, you know, and we do have, you know, collaborators that will obviously trigger their telescopes on the initial sky map here without waiting even for this one. I hope that was a good answer to your question.
Yeah, I think it was a good answer. Yes, thank
Yeah.
you very much. And just to clarify for our KNC astronomer here, so once we receive an update of the sky map, we usually also produce a new observation plan, especially if you see here after 4 hours of the sky map was completely different from the first one. So we just recompute the galaxy targeting that are inside well, I think it's in the 90% confidence region, but so yeah, we do update also the observation plan. Okay, thank you very much.
That makes sense.
Any more questions? Once, twice. All right, well, thank you, Andrew, for your talk. It was greatly appreciated. It was greatly enjoyed, and it was very insightful, especially with all that KNC does when following up on optical counterparts of gravitational waves.
Yes, thank you. I appreciate the invitation, and I wish everyone the best of luck with their searches. We're all very hopeful, right?
You got to do more work, make it easier for us.
Yep.
Thank you so much.